Hi, my name is Tim Marin, and I'm a product specialist for cables here at IGUS. And today we're going to discuss how to eliminate cable failure in moving applications. Today, our learning objectives are really based around the cable design and how it translates to or prevents failure. So, our learning objectives are 1, to review the common causes of cable failure, 2, learn how cable selection can eliminate downtime, reduce repair costs, and increase productivity. And 3, determine how cable design and installation directly affects service life and performance. To begin, we first need to dissect the types of cable that are available in the industry. We have static cables, flexible cables, and continuous flex cables. Static is typically for a one-time only installation, and then they never move again for the life of the entire cable. That's something that you'll see at your standard Home Depot or Lowe's. Flexible cables are easier to work with than static because you can usually bend them around, say the leg of a desk, or you can install them and then kind of change the position after it's been installed once, and it's not going to affect the cable poorly. And then with continuous flex, it's meant for exactly as it says, continuous flexing applications. It's constantly moving. We're talking 24/7, 365. Today, our focus is going to be on the continuous flex cables, as they are the proper solution for moving applications, especially those which require a cable carrier. For those unfamiliar with this product, a cable carrier guides cables in a path of movement that a machine makes while protecting the cable inside. When looking at cable carrier applications, we typically see linear movement. In the pictures we see here, there is a short travel or unsupported span on the left hand, and the right hand is gliding or long travel application. The reason we call it a gliding application is because the upper run of track glides on the lower part of the same piece of cable carrier. So because linear movements are most common, we'll discuss cables with that configuration in mind for this presentation. There are, however, other different styles of installation for cable carrier applications, and that includes vertical installations like the one you see, vertical hanging or standing, as well as some other specialized applications as well. That being rotary, where the cables are kind of in a circular configuration, and there are many, many more that we could go into and we've seen before and we've looked at. But when we're looking at the design of a cable, the primary installation types that we see are the linear cable carriers, so that's the ones that we'll focus on. Now that we've talked about the different types of cable as well as the different types of cable carrier applications, let's jump into our learning objectives. And the first one was the common causes of cable failure. So the first common cause of cable failure is excessive jacket abrasion or wear. And this happens when cables are pulled too tightly, which causes the abrasion against the crossbars of a cable carrier. This also happens when there's not enough space inside a carrier for cables to move freely. So if they're up against other electric cables or hydraulic hoses or pneumatic hoses, any other kind of media running inside the cable carrier, if you pack a cable carrier too tightly and you fill it with too much media, they can have abrasion and wear just by rubbing up against the other things next to it. And the third reason for jacket abrasion is that the jacket material is not intended for continuous flexing inside of a cable carrier. And that's kind of one of the big ones, because a lot of time if you're looking at a static cable or a flexible cable, because of their purpose, they're not specifically designed for the continuous flexing aspect. So that's usually where we run into the issue of the wrong jacket material, is when you've spec'd in or looked at kind of the wrong cable based on the industry. So the second cable failure we're going to discuss is jacket cracking and swelling. The first cause would be extreme temperatures, whether high or low. And generally the colder temperatures lead to material contracting, which is usually one of the main factors that leads to a cable cracking or the outer jacket cracking. The second reason is exposure to oils and or chemicals, like a coolant or something like that. If the material that makes up the outer jacket is not resistant to those types of media, then it will usually absorb that material and expand, and that expansion will usually end up with a cracking failure. So it may not be a noticeable failure at first, but it will lead to other problems later on down the line. And the third cause of jacket cracking and swelling is a smaller bend radius than recommended. And typically, again, that goes back towards the jacket cracking aspect. When we bend the cable too tightly inside of a cable carrier and it's not given the proper room to have a radius where the conductors are positioned in a way that they're able to operate without being under extreme pressure, then the cable can crack if it is underbent too much. So the next failure that we are going to discuss is conductor breakage. Here in the picture you can see it's quite obvious when you're looking at a conductor, but it's actually one of the hardest failures to kind of see to the naked eye, because obviously you are going to usually have a multi-conductor cable running in a continuous flexing cable carrier application. So you may not always see the conductor break, so you would lose electrical continuity, which is obviously kind of the most important thing and the main reason for having the cable. So when we're looking at that, the causes are a reduced cable carrier bend radius, and again, we can kind of see a pattern that this is the second time that if we have a cable that's underbent, it's causing a failure. Another cause is improper conductor strand design. If the stranding of the copper is too thin, it could break much quicker, or if it's too thick and it's not in the proper bend radius, we could have an issue there as well. The third cause of conductor breakage is the improper conductor or cable pitch length. So that is the length of kind of the twist and how it's designed. And finally, a conductor would break if it is not properly installed. If we don't have the right strain relief and it's not in the neutral axis and some other things that we'll get to later on about installation, we can see conductor breakage issues there as well. So the fourth cable failure is shield breakage. And this happens when the shield design and the pitch are not optimized for continuous flexing. Some might think that a looser shield pitch length or a looser angle on the shield may be more beneficial because in your hands it might feel a little bit more flexible or pliable. And while that is technically true, it won't actually lend itself to the proper design for a continuous flexing application. And it can also be caused by breakage and abrasion caused by continuous bending. So kind of the combination of the two, the wrong design and the wrong pitch, can cause your shield to break. And with a shield that breaks, the issue is not so much like the conductor breaking where you're losing electrical continuity, but the problem now becomes the purpose of the shield. The shield is there to protect against EMI, or electrical magnetic interference. And with the shield breaking, it loses that property and that ability to protect against EMI, as well as it could also damage the rest of the cable. It could poke outwards outside into the outer jacket, and it could also poke inwards inside into each individual conductor, which could then lead back into conductor breakage, which we've already spoken about. The final and most prominent failure we see in the field is corkscrewing. And this is when the cables are installed without space to move, kind of like I was talking before with jacket abrasion. Sometimes they're rubbing up against each other, and as you can see in some of the pictures here, there's just no room for the cables to move freely, and so they start having issues in that regard, or it could be caused from not having the proper strain relief, or maybe even when you're using a cable that's not designed for continuous flexing, the most common of which is a layered cable. And when you get to a certain number of conductors and you're talking about a certain situation with a cable carrier in a moving application, it can be very difficult to even strain relieve and install it properly if it's the wrong cable to not have it fail. Here we see a layered cable in motion, and you can see the length around the radius, and the radius again being that curved part on the right hand side of the picture. And those two orange lines that we see are kind of showing the different conductors and how they move inside of the cable. So one will actually have a shorter pitch, while the other on the outside radius of the cable will have the longer pitch length. And that presents an issue specifically for corkscrewing, because that means we have two conductors in the same cable that are essentially subject to a different amount of force. And that is one of the leading causes that can head towards corkscrewing. Now on this slide, we see a very similar setup, except you'll notice that the pitch length on each of the conductors in this particular cable are actually much shorter. And as you'll see the small orange lines running parallel on the outsides of the cable, you'll see that when it gets to that radius, that same point that we were looking at in the last slide, they're somewhat even, and that's because of the shorter pitch length, that the conductors are essentially subject to the same amount of force in the radius as opposed to the layered cable that kind of had one with a smaller and one with a larger radius that it was subject to. Now that we've gone through the things that cause cable failure, let's turn towards the design and see how we can actually prevent those failures. And actually, we already started with the last few slides beginning to touch upon the pitch length of the conductors. But let's dig in some more to see how the design can actually aid in extending the life of the cable. So here we see a couple of different examples of cables that are designed for continuous flexing applications. And we've highlighted some of the design features that actually make it really good for continuous flexing aspects. So the first part on the top left would be your bundled conductors. This is where we've kind of grouped them together in a way that it has a short pitch length, and it's essentially similar to what we talked about earlier when we bundle conductors together and you have that shorter pitch length of conductors. It's not subjected to different bend radii when it's in the continuous flexing movement. The second factor is the conductor insulation material. This is typically a high-grade plastic similar to what we use for the outer jackets as well, and that will help determine some of the different certifications that the cable will have printed on it later. Third, we have the optimized shield angle and pitch, which I shortly touched upon when we had the shield breakage as a cable failure. So when we look at it kind of from the positive side, we want to optimize the shield angle itself, and what we mean by that is we want the shorter or a tighter braided shield, and that will allow for as much, if not more, coverage of EMI protection, as well as continuously holding up in a flexing application that is running all the time. The fourth aspect of a good continuous flex cable design is the stress relieving center element. That cable core is actually a material that essentially holds the conductors in place where they are inside the cable. It allows the conductors to be properly positioned without falling to the center. If you were to use a certain flimsy filler material in the center or conductors instead of a material in the center, what you would end up with is a different bend radius for the inner conductors versus the outer conductors, or you would have the conductors falling into the center, causing different bend radii as well. So the fifth design aspect is the abrasion resistant jacket. We want a jacket material that's abrasion resistant simply because of the fact that we want to make sure that if there are other cables and hoses running inside, we don't run into the failure that we saw earlier in the presentation, as well as we're not exactly always sure what type of cable carrier that the cable is going to be inserted into. If we have a plastic cable carrier, there's a better chance that the abrasion resistance doesn't matter as much because the plastic won't be as hard or as harsh on the outer jacket of the cable. But if it's installed into a steel cable carrier, we could have some more issues, and they could happen much more quickly if you don't have an abrasion resistant jacket. So the more we can protect it up front and kind of have the right material that uses that outer jacket, we can move forward from there. The sixth cable design feature that we have for a good continuous flex cable is the gusset filled extruded inner jacket. And this is when it actually fills in the material, fills in all of the gaps in between the conductors. And you can see that on the picture all the way to the right-hand side, and where it's kind of pointing to it. There's no gaps whatsoever between the two conductors. And what that allows the cable to do is it holds those conductors tightly in place so the conductors don't have the ability to move against each other underneath the overall jacket. And when you're in a continuous flexing application, that can certainly happen if the inner jacket isn't extremely tight as it is shown here. And in a layered cable, a lot of times manufacturers use the loose tube extrusion simply because it's a cheaper method of making the cable. And while that may work for a flexible or a static application, it's certainly not optimal for a continuous flexing application. And the final design point we have is the optimized conductor design. And that is when we look at the actual thickness of the material, of the copper conductor itself. And when we're looking at the strands, there's some cables that use a thinner strand of copper, where other cables use a thicker strand or even solid copper for the conductors. With continuous flexing cables, we want to use kind of that medium grade to medium fine level, because we want to make sure it's thin enough that it's flexible and able to be moved in a continuous flexing cable carrier application where it's not breaking. But at the same token, we want it to stand up to those forces of being in a cable carrier in a very demanding application where it has to function, let's say every day for an entire year or several years in a row. At IGUS, we have over 50 years of experience with cable carriers, and we know the failures of cables all too well, which is why we decided to design our own line of cables for continuous flexing applications in 1989. And that line is called Chain Flex, as you can see on the slide in front of you. We took the design principles and factors that we just talked about and kind of examined all the different failure modes, and this is how we came up with our highly designed cable for the most demanding applications in the most extreme environments. Now we're going to discuss proper installation guidelines for putting the right cables into the cable carriers. So the first thing to think about with installation guidelines is actually the cable itself and not even dealing with the cable carrier. When you get the cable on site, you need to unspool it properly. And you're always going to want to pull from the top over the reel, as you can see in the top left-hand picture, where it shows the proper unspooling of a cable from a cable reel, and the top right-hand, it shows the cable reel on a stand. And in the bottom half, you see that you want to avoid pulling the cable over the flange and kind of while it's on the ground and just pulling it up and over. And the example that I like to use that I'm sure most of us have kind of gone through is when you coil up your headphones or earbuds or whatever you have. I usually coil it around 2 or 3 fingers, and then I put it down in the coil on my desk. And not thinking about the proper way to uncoil a cable, I usually just try and pick it up, and I've had my headphones tangled from time to time, and that's kind of the prime example, and hopefully a very short length example as opposed to some of the issues you could run into. If we're talking about, a crane application, we could be talking hundreds of feet of cable, so you definitely don't want to pull it up over the flange because that would be a lot of cable to kind of work with to respool and then unspool properly so that you can install it properly. So when it comes to installing the cables inside the carrier itself, we have a couple examples here of what to do and what not to do. Now, on the bottom left-hand picture, we can see that there's enough room in the chain for the cables to actually cross over each other while the cable carrier is running in the application, and that's definitely something we want to try to avoid. In the bottom right-hand picture, though, we also see that even though there's separation between the two cables, one of the cables is not pulled tightly enough and it's too loose, and that could cause other issues, but we'll talk about that in the next slide. So the top picture is the one we really want to use as our prime example of what our carrier should look like once we're installing the cables inside. So as I said before, we want to make sure that the cable is not too loose, but we also want to make sure it's not too tight. So the picture that we had kind of seen the overhead of before was where the cable was too loose next to a cable that was properly strain relieved and installed. So the too loose cable is kind of in that bottom right-hand picture where you can see it's along the outer radius. And what we're really looking for is the cable to rest in the neutral axis because we don't want it to be too tight along the inner radius that you can see in the bottom left-hand picture or too loose, because if it's too loose, that could also lead to corkscrewing cables and other failure issues. So now that we've talked about how to install the cable inside the cable carrier properly, we want to make sure that it's secure. So when we're looking at the ends of the cable and where it kind of comes out of the carrier, we want to make sure we're strain relieving both ends, because when you only do one end, it still allows for that other end to have some pull and give to it, which could cause other issues. It could either pull it too tightly because of the other end that it's connected to, and whether you're strain relieving it only on the moving end or only on the fixed end, you could certainly run into some issues with it. So we definitely want to make sure that we strain relieve both ends of all of our cables when they're in a cable carrier. So as I kind of mentioned earlier, we don't want the cables to cross over each other when they're running inside the cable carrier parallel to one another. And so for that, we actually have some guidelines as to which distribution rules to use, and whether that's vertical separation, kind of keeping the two cables apart because they're running in parallel next to each other, or whether it's horizontal separation because we have several smaller outer diameter cables running all concurrently in one carrier, and we need to shelve it so that we can fit all of them in properly where they're not crossing, entangling, and having any issues or problems. Now that we've discussed cable failure, cable selection, and proper cable design, I'd like to talk about IGUS's ChainFlex cables selection. So our ChainFlex cables are available from stock. We have 3 million feet of stock in our IGUS warehouse in East Providence, Rhode Island. We have no minimum quantities. You can buy 1 foot or 100 feet. And we have no cutting fees for the first 10 cuts of any part number. We have over 1,000 different part numbers available, including types such as control, data, bus, fiber optic, measuring system, servo, and robot cables. Again, all of which are specifically made and designed for use in a continuous flexing application. We also have a range of price points available to fit your specific and exact needs. If your application is relatively small or short travel, we certainly have a cable that will fit your need exactly, where you're not paying for the same typical design of, say, an application that would be several hundred feet long. This comes from our 7 different jacket option, where we have 7 different jacket materials that we make our cables with, and those correlate very closely to many different price points so that we can find the exact cable solution for your specific need without overpaying for an over-designed or over-engineered cable, even though we can cover the most demanding applications in the world. We also have the ability to harness cables inside a cable carrier system if you so choose. We also have several online tools available if you would wish to do it yourself. And this includes the ChainFlex product selector, which will help you choose the right cable series. We have the ChainFlex lifetime calculator, in which you can put your parameters for your particular application and get an estimated life cycle count based on our testing. And we also have the cable carrier configurator, and that helps with filling the carrier with the proper clearance as we spoke of before. So the information that we use to kind of back our online tools actually all comes from our state-of-the-art test lab. We have the largest test lab of its kind for continuous flexing applications, and there are many tests going on at the same time for short travels, long travels, rotary applications, and even torsional movements, to the point where we have 3 actual 6-axis robots performing standard functions so that we can test the torsional forces on our cables, because that is generally a different design. We also test different environments that we see out in the field, such as exposure to media like oils and coolants, as well as extreme temperatures. And a lot of times the material test done for the jacket material alone isn't enough to really provide our customers the peace of mind that they need when we're looking at using this cable in a continuous flexing application that is going to be moving all the time. We also have a 36-month guarantee that we can offer based on all of this information, where we guarantee any of our cables for 36 months or 10 million cycles, and all of the information on that can also be found in our catalog. So thank you for joining me today. I hope you learned a little bit about cable failures and why they happen and kind of what the most common ones are. as well as the cable design and why it's important to think about the design when you're looking at the specific applications. If you have any questions, you can feel free to post them here. Or if you think of them later on down the line, feel free to email me. I'm available at chainflex@igus.com, and we'll get to your inquiry as soon as we can, and we'd love to hear from you.